I'm good to go. Yeah.
Thank you, everybody, for coming. So we're very lucky to have Jason Liu here with us. He's coming from Brown University. He is a PhD candidate advised by Stephanie Salax. He is a regular at pretty much all of the big robotics venues, including Coral, IROS, ICRA, IJCA, you name it. He's probably got a couple publications there. And he's here to talk to us today about natural language at the intersection of robotics. He's got a lot of cool stuff going on with large language models, physical systems, home robots, you name it. So please join me in welcoming Jason.
Thanks so much, everyone, for coming. Before we get started, I just want to say thank you to Brad for hosting me and organizing on my talk. And thank you, Maria, for monitoring the Zoom. And okay, so my name is Jason Liu. I'm currently a PhD candidate at Brown University, doing research on robots and natural language. And today I'll be talking to everyone about the first step towards a robot that can use natural language, which is robotic language grounding. So my research is driven by developing intelligent robots that assist people. So I imagine the future where personal assistant robot will be universally accessible, and we'll see robots in many people's homes. And this video shows PR1 being teleoperated to perform many household chores. For example, vacuuming floors and tidy up a living room. And we have many ways to convey those tasks to robots. And they have each of them have their pros and cons. So first, we can use a graphical user interface or touch screen. It's very visual and very intuitive, but it's not very flexible. When we command robots to go somewhere or do something, we have to manually specify the right pose for the robot. On the other hand, we have code. It's very expressive and it's very flexible and ambiguous, but it's hard to use without training. So it's very hard for people who don't know how to code to command robots through a Python program, for example. And then we have natural language, which is a great way to communicate with robots. It's very expressive and it's very flexible and intuitive and very easy to use for human users, non-expert users. So we humans use natural language to communicate with each other all the time. And I imagine when we deploy robots in millions of homes, the most natural way for us to communicate with our robots is through natural language. And with the rise of large language models, we should be able to talk to our robot butlers, for example, easily. But so robot language is very great interface to communicate with robots. But how come we don't have natural language robots that we can talk to? How come using natural language to communicate with robots is so hard? So here are some challenges of using natural language. First, natural language, almost all the natural language commands we give robots are ambiguous. For example, if I tell the robot to go to the restaurant on Main Street, there might be two restaurants on the Main Street, McDonald's, KFC. Which specific restaurant I want the robot to go to? And robot needs to figure that out. And natural language is very complex. For example, if I can give this natural language command to robot, visit the bookstore on Main Street, but only after going to the Chase Bank. And after you enter the bookstore, move slightly to your left, find the orange magazine on the brown bookshelf in front of you. It's very expressive and natural language command. It specifies a long horizon task with spatiotemporal components at different levels of granularity. And it's also a compositional, which we can leverage to build our language processing system. So in this specific command, there are many referring expressions. For example, the bookstore on Main Street, the Chase Bank, also the orange magazine and the bookshelf in front of you. And another challenge is the natural language must be grounded. So for example, if I ask robot to go fetch the cup, robot must know what this that means in the physical, grounded into this physical environment. Because robot operating in the physical environments, we want the command we give to robot to be also grounded in the physical world. So in this, language grounding problem, we're going to address all those challenges. A quick definition of language grounding is we want to map, in this context, we want to map words in the natural language command to robot's decision process. For example, the perception space or like the action space. And even with current large language models, this language grounding problem is still very hard because there are uncertainties in both the human's mental state, what specific object human want, or the environment, where all those objects are in the environment. Okay, to solve this language grounding problem for robots, we want to answer two questions. First is what grounding representation we want to use, and second is how do we ground language to this representation of choice? And throughout this talk, gonna try to answer those questions. And also throughout the talk, we're gonna see robot demos. First, we can see some kind of navigation domain. So for example, go to the white car near the dumpster exactly 3 times. In addition, avoid the stairs in front of the apartment. And also a fetch or deliver kind of task. Go to the white desk, but only after the kitchen counter, because we want to pick up the juice bottle from the kitchen counter. Yeah, so those tasks are long horizon and they have spatial temporal component in it. So it's very hard to represent those tasks for robots. And I would first introduce a work that ground natural language from humans to a structured task representation. And the 2 papers in this category, one is grounding temporal commands in novel environments, zero shot. And the second one is grounding spatial temporal command, an extension of the previous work in novel environment in zero shot. And then I will talk about work we did, which exploit the structures to transfer skills for robot to solve novel tasks zero shot in the same environment, and present the work called LTL-Transfer. Finally, I'll talk about our survey paper we did, which reviews various language grounding papers. So not just grounding language to one specific representation, but grounding language to a wide variety of representation and put them on the spectrum from more symbolic approach to more high dimensional end-to-end kind of approach. Oh, sorry, my computer is froze. Maybe you can just restart PowerPoint. Store. What do I do on PowerPoint? You can unplug it. Okay, cool. Go back. Again. Yeah. Plug it in and share screen again. Oh, cool. Yeah. I will just wait. And just find your slide. Yeah, exactly. Okay, cool. Thank you. Okay, so the first work I'm presenting is about grounding natural language from human to structural representation. In this case, we're handling temporal type of command. some of the contribution of this work, just high level overview, we're grounding temporal navigational commands in normal environments without retraining on any language data. So with this enable us to unbox any drones in any cities and just start giving command to them, provided with semantic map and also the motion planning capability of the robot. And we tested this system in 21 novel cities and deploy in 2 indoor environments. And because we use a more structured representation of the command, robot were able to detect infeasible tasks and abort execution. Yeah, so go back to my original question. We try to answer what grounding representation to use. So maybe to answer that question, maybe we can think about some of the characteristics we want the structured representation to have. First, we want it to have unambiguous semantics. So we can unambiguously and precisely ground natural language command to for robot to understand. And then we want it to be able to capture some of the temporal constraints. For example, we may say, go to the store first, then go to the coffee shop, and always avoid downtown, maybe because of traffic. And the third property we want this representation to have is we want to be able to capture some of the spatial constraints the language command may have. For example, put the fork on the left side of the plate. And also, because the language is compositional, we also want this grounding representation to be compositional. So we can ground different component of natural language to different component of this grounding representation. And we also want it to provide this representation to provide some safety guarantees, because when we deploy robots in the human design environments, it's very important to make sure the action the robot takes is safe to humans. For example, it should be able to detect when a given task is infeasible, and also when the execution is violates some safety constraints, then the robot may decide to abort execution. Okay, so given all the properties of the structured representation, linear temporal logic seems to be a good candidate. A linear temporal logic, or LTL for short, is first invented by Bernoulli in 1977, and naively, it doesn't represent spatial constraints, but we can define propositions like can capture the spatial constraints, which I'm going to present in the second word. So in general, we want a grounding representation that can capture as many language commands as human can say to the robot. And the LTL actually represent a large portion of those natural language. And a survey paper in 2019 surveyed 306 robotics papers and discovered that 245 of them 245 tasks can be expressed in LTL. So in this talk, we can I'll use LTL as the grounding representation for natural language. Okay, so instead of boring everyone with the semantics of LTL, I'm going to give some examples of how LTL can represent the language command. So, for example, if I give this natural language command to robot, go to Walmart, but only after visiting the Chase Bank, I can ground this natural language command to this LTL formula. Finally, Walmart, the F operator means finally, and not Walmart until Chase. So because this LTL is compositional, we can ground different part of this natural language command to different part of this LTL formula. So go to Walmart will be grounded to finally Walmart, and only after visiting Chase, which means we shouldn't go to Walmart until we go to Chase. It's grounded to the second phase of this LTL formula. And this kind of new non-Markovian task, non-horizontal non-Markovian task is very hard for the numerical word capture, and but LTL is perfect for this. After we have LTL, we can translate it to we have off-the-shelf library that can translate LTL to Boolean automata, which is a state machine that keeps track of a task progress. So transitions in the environment are going to induce transition in the state machine. For example, if the drone starts in the initial state in the environment, also the initial state of the state machine, as it move to the Chase Bank in the environment, the state automatically going to transition from state 0 to 1. And then once it move to Walmart, the state machine going to transition from state 1 to the goal state 2. Cool. We just answered the first question. We want to use linear temporal logic as a grounding representation for natural language. And then how do we ground language to LTL? I'm going to talk about those two papers, grounding temporal language and spatiotemporal language. So first, I want to, before we dive into the details of those two papers, I'll first state some of the assumptions we make. First, we assume that the environment is static and fully observed. So robot knows where all the objects are, all the locations of the landmarks are, and then it can track its own states in the environment. And we assume we have a predefined set of propositions and their semantic information, both in textual or visual description, describe those propositions. And we can get the text description from, for example, OpenStreetMap, a map database, or get the visual description of the landmark from maybe Google Street View. And then we assume we have a labeling function that can map the environment state to the proposition that are true in the environment. For example, if the drone currently is hover around the Walmart, we know the proposition Walmart is true. Okay, for the first work, LAN to LTL, let's formally define the problem. So this system, we have take as input a temporal navigation command and a semantic map of the environment. And we want to output an LTL formula whose propositions are grounded to real-world landmarks. So for example, we can take it in this command, go to the store on Main Street, but only after visiting a bank. And also a semantic database describing landmarks in this environment. For example, we can describe Walmart by, it's a supermarket and it's on Main Street. And then we want to output a grounded formula, finally Walmart and not Walmart until Chase, where those propositions are grounded to the physical landmark defined in those semantic database. Okay, so it's a complex natural language. So where do we get started at grounding this natural language? We think about decomposing this problem into a few subproblems. The first one is called referring expression recognition. So we would fit the input, the natural language command into this referring expression recognition module, and they would identify the referring expression in this command. So in this example, the store on Main Street and also the bank. And the referring expression in this context means noun phrases or proper names that refer to some landmarks in the environments. So in this example, the store on Main Street would refer to Walmart, and the bank would refer to Chase in the environment. And to achieve this task, we use in-context learning with GPT-4. So we would do a prompt the GPT-4 model with examples. And also the query input command to extract for it to extract referring expressions. Okay, so once we have the referring expression, we want in text, we want to ground them into the propositions in the semantic database. So the next subproblem we're solving is called referring expression grounding. So to solve this problem, we use GPT-3 text embedding features to embed those referring expressions, the store on Main Street and the bank, separate into two text embeddings. And then we want to ground, also embed the textual description of the propositions into text embeddings, and then use cosine similarity to find the best match. So in this case, the store on Main Street best match to Walmart, and the text embedding of the bank is best matched to the text embedding of Chase. So we know the referring expressions are grounded into the propositions in the semantic database. And we assign symbols to those propositions, which we're going to use to lift the input command, which means we replace the referring expression by symbols, which make the next step easier. And once we have the lifted, so in this case, the store on Main Street is replaced by the symbol A, and the bank is replaced by symbol B. So the next step is to translate this lifted command to a lifted formula. Because we already replaced the referring expression by the symbols, the lifted command works with a smaller search space. And to do that, we fine-tune a relatively small large language model, T5 base, with a parallel data set we collected on lifted command and lifted formula. And then we can, because those symbols are already mapped to grounded propositions, we can just swap the symbol back with propositions. Now we get grounded formulas, finally Walmart and non-Walmart until Chase. And this formula can be used to provide reverse signal for any downstream planning algorithm or reinforcement learning algorithms that are compatible with LTL formula task specifications. Okay, so to test the generalization capability of this language grounding model, we defined 3 types of tests have increased levels of difficulties. First, we have alternate holdouts. So one example is in the training set, the system would say go to Chase, and then which is mapped to a finally Chase. And during a holdout test set, the system would be given unseen alternates with the Chase, but mapped to a similar formula had seen during training. And the slightly harder problem is robot formula holdout. So during training, our language ground system see some formulas, but we hold out certain type of formulas for test. For example, we've seen finally Chase and finally Walmart, and but during test we see a slightly harder or longer formulas from like similar categories. And the hardest test we have is called a type holdout. So during training, we see a certain number of LTL formula from certain types, but during test, we see an entirely new type of formulas. For example, during training, we have this nested finally formula, but during test, we see an entirely new operator until so finally Walmart and non-Walmart until Chase. And then we evaluate our lifted translation module on those 3 tests we came up with. So as we can see from here, the fine-tuned models perform quite well on the alternate holdout because they already seen most of the possible input command and also all the formulas. But as we increase the number of difficulty, we kind of see the prompt pre-trained model, the performance start to catch up. That's because when we fine-tune this model, we kind of restrict their operating domain, and they can only solve in distribution command. But the pre-trained model are better capturing kind of all the distribution type command. And as we have the hardest task, type holdout, the prompt GPT model actually performs the best. And then for the full system evaluation, we use the average success rate and evaluate on around 2,000 semantically diverse commands in 21 novel cities. One previous methods working on generalizing language grounding in novel environments called the CopyNet is encoder-decoder kind of model with attention, GRU and attention. It was only trained on 3 templates, and so the performance is quite poor on our data set. And then if you want to do a prompt a GPT-4 model for the entire end-to-end language grounding problem, going from input command to grounded LTL formula, it also doesn't perform quite well. But our new LAN to LTL system vastly outperforms those 2 baselines, both because we have more capable models and we decompose the problem nicely, and also we train on large data set. And then we demonstrate our system at the task planning level on a quadruped mobile manipulator. So one successful command here is ask the robot to visit a wooden desk exactly twice. In addition, do not go to the wooden desk before the bookshelf. Maybe you just want to pick out some books from the bookshelf. So the robot will go to the bookshelf first, and then visit the wooden desk twice. And so robot be able to handle this kind of command, temporal command in the real world, provided with a semantic map of the environment. And we deploy the system into 2 indoor environments and solve 58 robotic tasks. And then it'd be good to say some of the how robot handle some infeasible tasks. So because we ground in natural language to this structural representations, robot can actually abort execution if it detects infeasible tasks. For example, if a robot sees, if we give this command to robot, go to the counter but never visit the counter, which is kind of contradictory. So robot can detect this and decide to abort execution. And if we say to robot, find the kitchen counter, in addition, avoid doorway. For example, there's an environment constraints, like go to the kitchen counter, we had to go through the doorway. Robot can also detect this infeasible task and decide to abort execution. And then there are many cases they could be incorrect in grounding. For example, during training, we only see 5 type of visitation command. But in this case, we ask the robot to visit the counter at least 6 times. It would be auto distribution for our model, and it would ground to incorrect LTL formulas. And our system will be able to detect the semantic incorrectness of this LTL formula and decide to abort execution. Cool. I just talked about the first work. LAN to LTL grounding temporal command in novel environments. So the robot will be able to abort execution if it detects infeasible tasks. Okay, so the next work, we kind of extend our LAN to LTL work to handle not just temporal command, but also spatial temporal command. And we also wanted to be able to generalize into novel environments in both indoor and outdoor settings without retraining any language data. And here we were able to handle the 47 temporal patterns and the 19 spatial relations among objects or landmarks. And we were able to use like a multimodal kind of semantic information. Previously, we only have a textual description of the landmarks, but now we can have a visual description of the landmarks as well. So we have similar problem setup. So by the way, taking a spatial temporal navigation command and also semantics map the proposition in and are described by both text and images. And still we want the system to output an LTL formula whose propositions are grounded to real world landmarks. Cool. So for example, we can have this input command, visit a vegan restaurant west of the bakery, only then go to the red car to the right of the bakery. And here we have landmark described by both text and also images. So here the plant city and the wildflower are described by text, and this proposition car 0 are described by image of the red car. And through this LAN to LTL2 system, we still want to output the grounding formula where the proposition are grounded to the real world landmarks. Okay, so we still decompose this problem into a few subproblems because this natural language is pretty complex. The first one is we want to identify spatial referring expressions. Earlier, we identified referring expressions, but here we have a spatial referring expression recognition problem. So spatial referring expressions in this context means referring expressions are connected by spatial relations. For example, the vegan restaurant west of the bakery. Here, the referring expression, the vegan restaurant and the bakery are connected by the spatial relation west. And we, our spatial referring recognition model identified these spatial referring expressions and then put them into a structured representation, which we call spatial predicates, which is spatial relations followed by the referring expression. Yeah, so in this case, the vegan restaurant west of the bakery just means the plant city restaurant, and then the red car to the right of the bakery means the red car west of the wildflower. We use a similar approach like in context learning with GPT-4 to identify those spatial referring expressions. A large language model is very good at extracting information from complex language. And then once we identify those referring expressions, we want to ground them to propositions of the physical landmarks in the semantic database. We apply a similar approach where we use the text embeddings to ground the referring expressions, and then use text embedding to represent the referring expression, also use text embeddings to represent the propositions, and then use constant similarity to find the best matching. For the visual description in the semantic database, we first use a vision language model to capture this video. So for example, if I ask the vision language model, what's the most obvious object in this image, it would output like a red car or something. And we would embed this red car expression into a text embedding. Cool, and then we grounded the referring expression to landmarks in the real world. And provided with two grounded landmarks, how do we know they actually matches the spatial relations that connects the referring expressions? We define this problem as spatial predicate grounding problem. So for example, if I have the spatial referring expression, the red car to the right of the bakery, and we have the spatial predicate right and the red car in the bakery, we want to draw two vectors, one from the wildflower to the robot, another one from the wildflower or the bakery to the red car. As long as the red car lies in the half circle to the right of this green arrow, we know these two grounded landmarks fulfill this satisfy this spatial predicate. And we predefine a set of rules for will be predefined rules for a set of predefined spatial relations. Cool. And now the spatial referring expression are actually grounded to the landmark in the physical world. Again, we will send the symbol to those spatial referring expressions, and then construct the lifted command. Follow a similar approach, use the lifted translation model to translate lifted command to lifted formula, and then we swap the symbol back with grounded propositions. Cool. And then we did a modular evaluation on all the system modules. So here for the spatial referring expression module, where we use prompt pretrained GPT-4 model, you can see as the number of landmarks increases in those 4 city environments, it performs uniformly well. And for the referring expression grounding module, actually as the landmark increases, because there are more similar landmarks with similar descriptions, the grounding accuracy actually decreases. But if you just look at the top 10 candidates, actually the correct grounding within the top 10, the success rate is pretty high. And that's kind of what we need for the spatial predicate grounding module. It takes the top 10 candidate and from the referring expression module and try to find the best match, try to find the pair of landmarks that matches the spatial relations. And as we fit in the top 10 candidates, the spatial predicate grounding model also performed quite well in cities with different number of landmarks. And then the lifted translation module performed quite well if we do if we fine-tune the large language model. And we also apply a different approach called the retrieval augmented generation, RAG. As we increase the number of in-context examples we fit into the prompts, the performance increases. But as we max out the context window for prompt and GPT-4, the performance didn't match the fine-tuned model. But I see it's a feasible way of, instead of fine-tune our models, we can actually use just prompt already pre-trained model that can handle more diverse type of commands. Okay, so we also evaluate the same system. We also did full system evaluation using average success rate in 20,000 semantically diverse commands in 4 city environments with 5 Cs. If we did a ablation study, so if we just using image and text alone description of the propositions, the system doesn't perform quite well. But if we use both language and text, text and image description of the landmarks, it performs really well. Because for example, if I want to say some landmarks is better described by a text description. For example, I can just use the name of the restaurant. For example, go to a McDonald's, and that's best described by maybe a piece of text. And for some landmarks, maybe it's best described by image because we don't have those things in the text semantic database. For example, like a red car. And then we deployed the same system without modification in both indoor and outdoor environments. Here I'll show one example of the outdoor environments. Go to the white car near the dumpster exactly 3 times. In addition, avoid the stairs in front of the apartment. So here the robot would take a different path, actually around the another building to avoid the stairs, and then go to the downstairs 3 times. It's a long horizon command. It contains both the spatial component and also temporal component. The spatial component here are highlighted by blue. The white car near the dumpster, also the stairs in front of the apartment. And the temporal component highlighted by red that go to exactly 3 times in addition avoid. Okay, cool. And we also deploy the same system for the indoor and outdoor environment to solve like around 25 tasks and provide the robot with the semantic map of the environment. Cool. We just talked about two language grounding systems. The second one is grounding spatial temporal language command in normal environment without retraining on language data. And we were able to capture 47 temporal patterns, the 19 spatial patterns. And we were able to use multimodal semantic information and deploy the robot on a real system. And now, so once we ground natural language to the structured representation, what are some of the advantages of using this structured representation in this case, linear temporal logic? I'll talk about this skill transfer paper we did. Some of the contribution is we can leverage the compositionality of this structured representation to reuse learned policies to solve novel tasks in the same environment. And the robot would able to abort execution if it detects the skills I learned during training is not enough to solve this novel task and not take any dangerous action. Yeah, so on a high level, we reuse learned policies to solve new task, zero shot. For example, during training, we learned how to solve two tasks: fetch the juice bottle and fetch a textbook. And during training, if we ask the robot to fetch the textbook first and then the juice bottle, in zero shot, the robot can just sequence those two skills together and achieve this command. And as the input, we would take this system would take a set of training LTL tasks and a novel test tasks, and then a set of proposition known for the a set of known propositions for the landmarks, and output a sequence of skills that solve the test task. Here we relax the assumption we had before. We assume the robot doesn't know the transition dynamics. Okay, and this algorithm has 3 steps. First, we will learn a policy for state-centric options, and then we will decompose those state-centric options to transition-centric options, and then transfer those skills to solve novel tasks zero shot. Here, the state and the transition means the state and transition in the state machine we talked about mentioned earlier, not the state transition in the environment. So just to run through an example of the training and testing. So here we will take as input the training task, finally juice and final desk, which means we can go get the juice or go to the desk in any order in this environment. And we would first translate this training task to a reward machine graph. So the automatically use off-the-shelf library. The nodes represent reward machine states, which encode the progress of the task. And then the edges are labeled by Boolean formulas. If fast satisfied, will progress the reward machine from one state to the next state. Here, so we leverage the compositionality of this reward machine and decompose this training task into 3 subtasks, which are encoded in state 0, 1, and 2. State 0 just means the robot hasn't done anything. State 1 means robot has picked up the juice. And state 2 means robot has gone to the desk. And then we can use any R algorithm that is compatible with LTL tasks to learn a policy to solve each subtask. So we would learn a policy from state 0 to going out of state. So we call this transition-centric option. So depending on the proximity of the robot to different landmarks, the robot can decide to go to state 1 or state 2. Similarly, we learn a policy to transition from state 1 to state 3, also policy to transition from state 2 to state 3. And then once we have those state-centric options, we want to decompose them into transition-centric options to target specific edges in this reward machine. So for example, for the policy we learned for state 0, which can transition the robot from state 0 to any of the 2 states, 1 or 2, we decompose it to a policy that would, a skill would translate robot from state 0 to a transition robot from state 0 to state 1 if robot is close to the juice in the environment. And the second policy would transition the robot from state 0 to state 2 if robot is close to the desk in the environment. And while robot is try to target specific edges of the reward machine, it maintain the self loop. and until like they go to a specific landmark and it triggers the edge transition. Okay, cool. So let's say we learn skills, transition entry skills from those two training tasks. Finally book, which means get the book, final juice, and final desk, which means go to get the juice and then go to the desk. Let's say we're given this novel test task, which is finally book and final desk, which means we want to get the book and then go to the desk after we get the book. We also transcribe this LTL task into a state machine. And then we can look at the edges of the state machine to transition from 0 to 2, from initial state to the goal state. We'll go through two transitions, first from 0 to 1, and then from 1 to 2. And then we look at the training edges we have. We are learning the option to solve this training edge from the first training task. So we can apply these skills to transition robot from 0 to 1 in the test task 0 shot. And then once we get to the book, we robots in the second in state 1 of the test automata, and we look at the edge from 1 to 3. We see that okay, we already learned the option to transition to achieve this transition from the second training task, and we induce that option, so the robot would go to the desk. Yeah, and this option would command robot to go to the desk. Yeah, so we evaluate our system in simulation on LTL tasks with a very number of difficulties, going from hard and mixed, which means they're actually a failure state of those tasks, to like a soft, strictly soft or no other kind of task, which means there's no failure states in those tasks. And compare our method with 3 baselines. One is called LTL to action, which more like a end-to-end kind of system where they encode LTL into a graph neural networks. Also LOPO, which use RL to learn from a set of training tasks, and but did not do the decomposition like we did. And also the random policy that would take 500 random steps. So as we can see from the plot, our system outperformed all the baselines, especially on the hard tasks, hard and mixed tasks, because there are actually failure states in those tasks. Because our system were able to identify those the policy learned during training are infeasible to solve those tasks and abort execution. And the other system would actually take some random actions in unknown states and cause some violation of safety constraints. And then we also deploy the system on the task planning level of our quadruped mobile manipulator to solve this task. For example, we solve this task finally counter and finally white table, which means go to the counter, but only after the kitchen counter. Go to the white desk, but only after the kitchen counter. In this case, robot would go to pick up the juice bottle at the kitchen counter and deliver to the white desk. Okay. Yeah, again, we deploy our system on to solve 100 novel tasks. Here, 50 of them are shown here just by learning skills from 20 training tasks. And 1/3 of them are actually fetch or deliver the kind of task, and 2/3 of them are navigation tasks. And yeah, during execution, robot were able to abort whenever the learn options are not sufficient to solve the novel test task, which enforces some safety guarantees. Yeah, so yeah, we just presented this skill transfer work, and we should leverage this compositionality of LTL task specification and to reuse policy to solve novel tasks in the same environment, and we're able to abort if the learned policies are not sufficient to solve the novel task. Yeah, so we just answered those 2 questions. LTL is one candidate grounding representation we can use, and we're able to ground the both temporal and spatiotemporal command to LTL and leverage composition and LTL for generalization. But LTL is not just LTL can cover everything. And we also did this survey paper of various language grounding representations. And then we put them on a spectrum from on the right side, more symbolic kind of approach, where they are more discrete symbols and they're more structures and more bias, but they have unambiguous semantics. And they some of the logic representation provided us with some variability and also interpretability. And then on the left-hand side of the spectrum, we have a more high-dimensional embedding, end-to-end embedding kind of representation. Here, the representation are more continuous. They have less structures, which doesn't require manually define those symbols, but they have more variance. But they are more adaptive to new environments. But we will lose some of the interpretability and the verifiability of the symbolic approach. And some method in the middle, we can ground natural language to, for example, predefined skill descriptions, also natural language of images of subgoals. Cool. And throughout this talk, I just talk about this robotic language grounding problem, where we can ground natural language from humans to a structured representations in those two papers, LTL, which ground temporal command, and the LTL-2, which ground spatiotemporal command, and leverage the structure of this representation to reuse policies to solve novel tasks in zero shot in this LTL-Transfer paper, and also a survey of all the many of the robotic language grounding paper post LLM, and talk about some of the trade-offs between the symbolic representation and the embedding representation. Yeah, so some of the other work I did is during my undergrad, I did some robotic manipulation work where we developed a tool system that use vision-based kind of a system to do both grasping and parallel jaw using parallel jaw gripper and also suction cup to do a bean picking kind of task. And some of the future work I'm thinking about pursuing is we can relax some of the assumptions I made in this talk. First of all, instead of just using natural language to communicate between human and robot, we can have more modalities. For example, we can use demonstration to show what we want the robot to do. And we can also use gestures to point it to the objects we want the robot to pick up, for example. And then we also want to enforce robot safety at both a task and motion level, and but without losing the interpretability of the robotic system. So we want to be able to predict and detect and reason about and explain and recover from failures. Because when we deploy robot in human environments, inevitably robots are going to fail, but we want to be able to handle those failures properly. And also have this feedback loop going back from robot to human, and where robot can ask clarification questions to disambiguous the command, or can provide explanations of its behaviors. Yeah, so thank you so much for listening to my talk. Yeah, I'm happy to answer any questions.
Let's thank the speaker and start the question. Any questions from the audience?
Oh, yeah.
Can you provide some information on how you go from LTL to, say, real world motion planning? Most of the work was like getting from natural language to LTL.
Yeah.
But what goes there?
Great point. Most of the work here is focused on grounding natural language, which means just go from natural language to LTL. But what happened after that is we first transcribe LTL to an automata, which we can do a product MDP, so we transcribe LTL to a state machine, and then use some off-the-shelf library, and then do a product with the environment MDP to construct a product MDP. And then we use some planning algorithm to figure out some of the locations we want the robot to go to. And then we use off-the-shelf motion planning to navigate between those locations.
I have a related question. How is the robot identifying objects in the environment? And what happens if there's confusion between the identity of those objects?
That's great question. So to identify those things, we'll use SLAM to build a semantic map of the environment already. So robot knows where all the landmarks are, and also the semantic description of those landmarks. Yeah. And then if there's an ambiguity, so that's some the future work I'm thinking about tackling. So if there's for example, multiple juice bottle on the counter, which one do you want the robot to pick up? Or if there's uncertainty of even one juice bottle, the location of one juice bottle, how the robot handle this uncertainty? I think about the define some probabilistic symbols, yeah, to capture those uncertainty in the environment state. Yeah, thank you for the question.
In the safety section of the LTL, the first part,
Uh-huh.
you mentioned that one of the stopping criteria is when there is a grounding that is not
Yes.
meaningful. I
Right.
forget the exact word you
Yeah.
used. So what does that mean concretely? Like, is it syntactically incorrect?
Exactly.
or-
Yeah, so there's two type of grounding errors, right? Like syntactic errors, so you just output like a LTL doesn't make sense syntactically. That kind of thing we can capture. So if we can detect syntax errors in LTL formula, and then just decide, okay, because the grounding is already wrong, we just don't do anything moving forward. And also there's also semantic incorrectness. Yeah, so this is very hard, and the previous work hasn't captured that, but it's something I'm exploring in my future work.
Yeah, I was gonna ask you, is there a measure of confidence in the prediction?
Yes, so a general approach I think about taking is to have the probability distribution over possible things. We have probability distribution over the possible LTL syntactically correct LTL formulas. If the probability distribution is very flat, we can have robot ask human question, or do you want me to achieve this task versus that one? But if it's very skewed, that means robot's kind of confident what kind of task you want the human model robot to do. Yeah, thank you for the question. Yeah.
So in that LTL-Transfer section, you
Uh.
also talked about how it's able to abort the task if it determines that the skills that it's learned are
Yes.
not sufficient.
Yep.
So how does it decide that?
Right. Great question. So there's some low level detail I climb through. So in this case, for example, if we'll do some kind of edge matching. So we have this set of test edges in the test task for the test task, and we have a set of edges for the training task. So let's say, for example, if from state 1 to 2, this blue edge is not present in the training task, we know, okay, we haven't learned anything to solve this to induce this transition. So that's when we decide, okay, robots should stop doing anything because it's in an unknown state. Or yeah, thank you for the questions.
Any other questions? Do you have anything else? All right, so let's let the speaker again.
Okay, thanks so much. Okay.